Okay, in today's session, we will see the rest of transmission of heat. We learned the basics of transmission of heat in last session. In the last session, there are three modes of heat transfer. First one is conduction. We learned about conduction in the last session. Then there is convection. Then there is radiation. Okay, and there is one point that I missed in the last class. Actually, this is to be seen in another topic, but anyway, I'm telling you a brief idea. Right? Have you heard about anomalous expansion of water? Anomalous expansion of water, you'll see that in thermal expansion, anomalous expansion of water. Okay, for the moment I'll tell you the question only. This is an important question. Okay, during winter time, lakes get frozen. Now if you go to the North Pole or South Pole, you can see that the lakes get frozen during winter time. Why is it happening? It is because of something called anomalous expansion of water. What is anomalous expansion of water? I'll tell you all those things later on in thermal expansion. Okay, so there is something called anomalous expansion of water which causes water on the surface of lake to freeze. Okay, last year, even in Netherlands, in Amsterdam, the canals, when canals were frozen, actually they get frozen only at the top. Yes, aquatic life survive. Yeah, that's right. Okay, so if you take a lake like this, only the top layer gets frozen. Only the top layer gets frozen. Below this, you'll have water at 4 degrees Celsius. That is the previous question. It was the first question in one of the entrance examinations. What is the temperature of water just below a frozen lake? Frozen lake. Actually, the surface layer alone is frozen. If you break it open, you can see water underneath. Okay, living organisms can survive underneath. That is actually one way of protecting, nature's way of protecting the organisms underneath, fish and plants and all those things. Okay, anyway, how does it happen? I'll tell you about it later. For the moment, just know that there is something called anomalous expansion of water. Anomalous, it is some sort of an anomaly, discrepancy, anomalous expansion of water. It is like water behaves in a different way compared to other substances when it comes to the case of thermal expansion. There is something called thermal expansion in which substances expand upon heating, but water behaves differently. Water has a different behavior. We'll see that in next session. Anyway, just know that there is something called anomalous expansion of water, due to which during winter time the surface of a lake or a canal gets frozen. Surface gets frozen. Surface is ice. Like you have a huge block of ice on the surface layer, but just below the surface you got water at 4 degrees Celsius. Water at 4 degrees Celsius. 4 degrees Celsius. Okay, and you have an equation here. You have to learn this equation. Rho L divided by 2k theta into y2 square minus y1 square. What is this? This is the only equation to be learned here. Actually, it is the end equation of an integration. You will need this equation as such for JEE exams only, but for NEET, I'll tell you what you need. Okay, rho is density of ice. L is latent heat of ice, then K is thermal conductivity of ice, theta is the temperature outside. Okay, and y2 square minus y1 square. Y1 is, this is actually the time taken for the ice to grow in thickness from y1 to y2. So initially, if it has a thickness of y1, ice has a thickness of y1, it is growing actually. It is adding ice, right, every second. Ice is growing in thickness. What is the time taken to go from y1 thickness to y2 thickness? This is an important point. T is proportional to y2 square minus y1 square. For NEET examination, you just need to know this relation. The first relation is not required. Time taken to grow from y1 thickness to y2 thickness. This is important, very, very important. So many times asked. Previous ITJ equation as well. So actual equation is time taken is equal to rho L over 2k theta divided by y2 square minus y1 square. That is the time taken to go from y1 to y2. But this equation as such won't have to be used unless you are writing JEE advanced examination. Okay. So rho is density of ice, L is latent heat of ice, K is thermal conductivity, and theta is temperature. And y2 and y1 are the thicknesses. For the moment, you just know this. T is equal to y2 square minus y1 square, because they'll ask you to find the ratio of T1 to T2 to T3. What is this? Y1 to y2, this thickness. Y2 to y3. If you want, this is for T1. I can write what? T1, you can write a constant into y2 square minus y1 square. And for T2, it is what? K into y3 square minus y2 square. T4, T3, it is what? K into y4 square minus y3 square. And if they ask a question, it's going to be the ratio of these. That's it. You can directly put y1, y2, y3 values and then find out. Okay, did you understand this? This is very, very important. Okay, I'll have a quick review here. This is anomalous expansion of water, which you will see in thermal expansion. Substances expand upon heating, but water shows a different behavior. Okay, water has a particular characteristic, and this is called anomalous expansion of water. It is a different thing, right? Anomalous water expands in a different way compared to other substances. Okay, so it is because of this that lakes get frozen during winter. If you go to the polar regions, during winter time, they even have deep fishing there, no? If you they break the ice open, and then underneath you can fish. Okay, and the surface layer get frozen. So that's a huge layer of ice formed over the lake. Underneath, water will be at 4 degrees Celsius. Here the water is at 4 degrees Celsius. Like I said, that's a previous question. What is the temperature of water just below the surface of a frozen lake? It is 4 degrees Celsius. Okay, right here it is 0 degrees Celsius because that is in contact with ice. Okay, that is still in contact with ice, but this is 4 degrees Celsius. If you take the water underneath, it is 4 degrees Celsius. If they particularly ask what is the temperature of water underneath a frozen lake, it is 4 degrees Celsius because water has maximum density at 4 degrees Celsius. You will understand it later, don't worry. Water has maximum density at 4 degrees Celsius. That is seen in another module, thermal expansion. Anyway, here the temperature is 0. Here the temperature is theta degrees Celsius. Theta degrees Celsius. Okay, temperature outside is theta degrees Celsius. And then, you know, this is the temperature time required for ice to grow. Ice to grow. Actually, ice is growing here, no? Growing in thickness. The equation is rho L over 2k theta into y2 square minus y1 square. This equation won't be needed. I just gave the equation. That's it. Rho is density. L is latent heat of fusion. Yesterday we learned latent heat of fusion. K is thermal conductivity. Theta is temperature of outside. Temperature outside. Y1 and Y2 are initial and final thicknesses. Forget about this equation. You know, you can take T as proportional to all these guys are constants, right? So rho is proportional to T is proportional to y2 square minus y1 square, or T1 is equal to K into y2 square minus y1 square. T2, if I take K into y3 square minus, this is time taken to grow from y1 to y2, time taken to grow from y2 to y3, time taken to grow from y3 to y4, and you'll be asked to find the ratio here. Is that clearly understood now? So we have finished the mode of conduction, heat transfer by conduction. Next is convection. Like I told you, convection, you don't have any numericals. There is only one equation, Q by T. Rate of heat transfer is equal to H into A into T minus T0. Heat lost per heat transferred per second is H. H is called convection coefficient. A is surface area of the liquid. T minus T0. T is the temperature of the liquid. T0 is temperature of atmosphere. But this won't be required 100%. Even for JE, you won't require it. Okay, so I'm not teaching this for the moment anyway. You know, convection, you don't have any questions there. Convection, you know, yesterday I told you, heated up air goes up, you know, cooled air comes down. There is a circulation, right? Just like heart is pumping blood, that is again convection current. Okay, convection current. So convection is basically movement of fluid. This happens only in fluids, liquids and gases, right? What are fluids? Anything that flows is called a fluid. Okay, fluids are actually liquids plus gases. Liquids and gases together are called fluids. And convection happens only in fluids, convection. You just have to know a couple of points here. That's it, convection. What is convection? Like I said, if air is heated up or water is heated up, that goes up and that is replaced by cold air from top, right? So that is like a circulating current. Again, heart pumping of blood by heart, that is again convection. Okay, so there are two types of convections: forced convection and natural convection. Forced convection and natural convection. There, if you want, you can take a note of this: forced convection, then natural convection. Now hot air moves up, automatically that is replaced by cold air. Sea breeze and land breeze. Sea breeze, you learned in detail. Sea breeze, land breeze, land breeze. Okay, these are examples for trade wind, trade wind, trade wind. That's a particular kind of wind that actually blows from polar regions to the equatorial region. There is a particular kind of wind that blows from polar region, north pole to equatorial region. That's called trade wind. These are all due to convection. That's all about convection. Did you understand? So we have seen two types of heat transfer. First one was conduction. There were a couple of equations. There are so many questions asked from that part. Convection does not have any numerical, but radiation is also important. There are a couple of laws, very important laws: Wien's displacement law, Stefans law, and Newton's law of cooling, based on which you may have questions. Okay. So before going to this, I'll tell you a brief idea of radiation. What is radiation? In conduction, you needed a medium, but the medium was not moving. The particles were not moving. Do you remember? In conduction, a medium was required, but the particles were not moving. Only heat was being transported. Just like you transfer something to the 10th guy standing in a row. Okay, right. Yes. In convection, the medium itself was moving. Right, the particles were moving. In conduction, medium was there, but medium was not moving. In convection, medium was there, medium was moving. In radiation, no medium is required at all. No medium is required, because like I said yesterday, sun is giving energy by way of what? Not by conduction, not by convection, because in between us and sun, there are huge void spaces, empty spaces, through which energy is coming in, right? So that must be what? That must be radiation. And this actually falls in this wavelength, 7.8 into 10 power minus 7. You have to learn this, meter to 4 into 10 power minus 4 meter. You have to learn this frequency range, wavelength range. Okay, and these are called heat waves or thermal radiations or infrared, because these wavelengths actually belong to infrared region of electromagnetic spectrum. There is something called electromagnetic spectrum. You remember what it is? Electromagnetic spectrum. Electromagnetic spectrum, some waves which have identical characteristics are grouped into a certain spectrum, certain band, and that is known as electromagnetic spectrum. They do not require a medium, no medium to travel. So radiation, no medium to travel. But for heat transfer through radiation, no medium is required. Okay, it can actually travel through empty space, void spaces. Then it travels at the speed of light, 3 into 10 raised to 8 meters per second. And then wavelength range is written there, wavelength range, 7.8 into 10 power minus 7 to 4 into 10 power minus 4. This is the wavelength range for radiation. These are actually infrared waves, infrared. There are different waves in electromagnetic spectrum: visible, infrared, ultraviolet, gamma rays, X-rays, microwaves, radio waves. These all these are what? All these are what? All these are different waves that belong to electromagnetic spectrum, right? They all belong to electromagnetic spectrum. They are all electromagnetic waves. Okay, so that is the first thing about radiation. I'll tell you one more time. Radiation is the last mode of heat transfer. This is supposed to be the most important as well. Okay, so no medium is required. Sun has been giving energy for us, right? And the velocity is 3 into 10 power 8 meter per second, just like light wave. And then wavelength ranges how much? Wavelength ranges 7.8 into 10 power minus 7 meter to 4 into 10 power minus 4 meter. So you can find frequency, obviously. If they ask you to find the frequency range, take nu is equal to c by lambda. Hope you remember, nu is equal to c by lambda. And these are called infrared waves, okay? All right, these are the characteristics, okay? And, if you take a surface, just imagine a surface is there and a ray of light is falling on it, or heat radiations are falling on it, heat radiations. These heat radiations are going in 3 different ways. Okay, a part of it is being reflected, another part is being absorbed, another part is being transmitted. Okay, there are 3 components for the incident radiation. So what are the situation we are in? We have taken a body, we have taken a surface. Okay, we have taken a surface, and there is an incident radiation which I can call Q. The amount of radiation incident is called Q. All right, and a part of it is reflected. So reflected component is called QR. Reflected component is called QR. This is QR. And there is absorption. So that is called QA. And then there is transmitted component, that is QT. All right. So I can write three things here: reflectance. Reflectance is what? Reflectance is QR divided by Q. That means the amount of energy reflected divided by the amount of energy incident on it. So what percentage of incident energy is reflected? That is called reflectance. Okay, I'll tell you. Then next is absorptance. Absorptance. What is absorptance? Absorptance is QA divided by Q. Absorptance is QA divided by Q. The amount of energy absorbed divided by the total energy incident. Then there is transmittance. Okay, transmittance. That is QT divided by Q. Transmittance. The amount of energy transmitted divided by the total amount of energy incident on it. So if you add them up, what do we get? QR by QA, or QR by Q plus QA by Q plus QT by Q. What is this? This is equal to I'm sorry. If I take LCM here, it is Q. On numerator, it is QR plus QA plus QT. What is QR plus QA plus QT? QR plus QA plus QT is nothing but Q itself. That is equal to 1. So this is called reflectance R. This is called absorptance A. This is called transmittance T. So R plus A plus T is equal to 1. R plus A plus T is equal to 1. Okay. And if you have A is equal to 0, T is equal to 0, A is equal to 0, T is equal to 0 would mean R is equal to 1. That is a perfect reflector. R is equal to 1, 100%. Now, if R is equal to 0, T is equal to 0, we have A is equal to 1. That is a perfect absorber. Perfect absorber. That is called a perfect black body. Perfect black body. I'll tell you about it later. Perfect black body. Then if A is equal to 0, R is equal to 0, that is T is equal to 1. This is called a perfect transmitter. Perfect transmitter. Okay, I'll revise these points one more time. We have a surface here. This is a body or a surface on which radiations are falling. Look at that. These are thermal radiations. Okay, the amount of energy falling on it. Just give me a second. Okay, continuing. We have a surface here on which Q amount of radiation is falling. Amount of radiation falling is Q. All right. Total amount of radiation falling is Q, a part of which is reflected. That is QR. Reflected component is QR. Absorbed component is QA. And the transmitted component is QT. There are 3 components here, right? And then I'm taking QR by QA. Amount of energy radiated, amount of energy reflected to amount of energy falling on it. That is called reflectance. That means out of the incident radiation, how much is reflected? Similarly, absorptance, how much is absorbed? QA divided by Q. And then how much is transmitted? Transmittance, QT divided by Q. So this is reflectance, this is absorptance, this is transmittance. And then if you add them up, QR by Q plus QA by Q plus QT by Q is what? On denominator, it is Q, QR plus QA plus QT. What is QR plus QA plus QT? QR plus QA plus QT is nothing but the total incident radiation, right? Total incident radiation splits up into 3. QR plus QA plus QT is actually Q. So Q by Q is what? Q by Q is 1. This is called R, reflectance R. This is called absorptance A. And this is called transmittance T. And this is Q by Q is equal to 1. R plus A plus T is equal to 1. And if A is equal to 0, absorptance is equal to 0, transmittance is equal to 0. You know, if both are 0, absorptance 0, transmittance 0, R is equal to 1. R is equal to 1. That is a perfect reflector. And then R is equal to 0, transmittance is equal to 0. If R is 0, T is 0, A will be 1. A will be 1. That is perfect absorber. A black body, perfect black body is something that absorbs all radiations. Okay. Perfect black body. So it will appear in black in color. Okay. It will appear black in color. Perfect black body. I'll tell you about perfect black body now. Okay. And then if A is equal to 0, T is equal to 0, A is equal to 0, R is equal to 0, that will leave you with T is equal to 1. T is equal to 1 means perfect transmitter. Okay. Now, hope you understood these points. I'll tell you a couple of more points. Okay. There is something called, okay, I'll tell you about perfect black body now. What is perfect black body? Like I said, perfect black body. What is a perfect black body? I told you its absorbance will be equal to 1. That means it absorbs all radiations. Okay. When heated up, if you heat it up, when you heat it up, it emits all radiations. It emits all radiations. I'll tell you one more time. What is a perfect black body? There is something called Ferri's black body. Ferri's black body, which is almost a perfect black body. Look at this. It is actually a spherical cavity like this. With a hole here. Spherical cavity with a hole. And then there is a wedge over here. What happens now? A radiation entering this will fall here. That will undergo multiple reflection and captured inside. Okay. So any radiation entering inside will be totally absorbed. Okay. And if this is heated, it will emit radiation. It will start emitting all radiations. This is the example for perfectly black body. Sun is a perfectly black body. And you know one thing, our body is emitting radiations all the time. You know that? You can't see that because they are invisible. Any body above 0 Kelvin, above absolute zero, any body above absolute temperature, any body which is kept above absolute temperature, absolute zero, will emit radiations. Understood? It will continuously emit radiations. Our body is emitting radiations, right? When you have fever, there are certain other valence being emitted because your temperature is higher. Correct? See, every body at all temperatures above absolute zero emit radiations, emit electromagnetic radiations, thermal radiations. Okay. Did you understand? That's an important point. You have to write. You have to write it down somewhere. All bodies above 0 Kelvin. All bodies kept at above 0 Kelvin emits thermal radiations all the time. Thermal radiations. Even now, all of you are emitting thermal radiations, but they are infrared. They don't belong to visible spectrum, so you can't see them. Okay, you can't see them. Anyway, this is a perfectly black body. Ferri's black body. Lamb black is another example for black body. Lamb black. Okay, anyway, forget about it. You just have to know this. Ferri's black body. And sun is an example for perfectly black body because sun is at a temperature of 6000 Kelvin and it is emitting all radiations, all possible radiations. Okay. And this is what I said about perfectly black body. You just have to know these things. Number one, what is a perfectly black body? Absorptance is equal to 1. That means it absorbs all radiations, all possible radiations. And then what else? When heated up, if it is heated up, it emits all types of radiations. An example is Ferri's black body. This is how Ferri's black body looks like. Okay. There is a spherical cavity inside which we have a wedge. This is a wedge like a blade. And then if a radiation falls here, look at that, it falls here, no? That gets reflected, it falls here, gets reflected, again reflected. It is actually totally captured inside. Okay. So whatever radiation comes through the hole will be captured inside this. And if you heat this up now, it will start emitting radiations. This is black body. Did you understand? So we have seen many things so far. Anomalous expansion of water, then growth of ice on a lake, the equation for it. T is proportional to y2 square minus y1 square. Then convection, applications of convection. Equation for convection is not needed anyway. Radiation, the characteristics of radiation. Then we learned black body, absorptance, reflections, and transmittance, right? Okay, I'm going to tell you something. If you take a body, this is a surface, okay? Surface. The amount of energy emitted, I take a unit area on top of this. Unit area means what? 1 centimeter length, 1 centimeter breadth. Okay. And the amount of energy radiated, per area per second, the amount of energy radiated per area per second is called spectral emittance. So what is spectral emittance? You just have to know the term. That's it. There won't be numerical on this. The amount of energy radiated per area per second. That means from unit area of a body per second for one wavelength. This is for one wavelength, only for one wavelength lambda. And for all wavelengths, lambda all, we have another term that is called total emittance. spectral emittance and total emittance. Okay, this is called monochromatic emittance also. You just have not the terminology here, that's it. Okay, I'll repeat one more time. We have a body that emits radiations. I told you that any body at temperature above 0 Kelvin will emit radiations. So I take such a body and I draw unit area on it. Unit area, this is unit area with 1 centimeter length and 1 centimeter breadth. And you count the amount of radiation. You take the amount of radiation transmitted from it, emitted from it, the amount of radiations emitted per area from this area per second, the amount of radiation emitted per area per second for one wavelength, one particular wavelength. That is called spectral emittance or monochromatic emittance. And what is total emittance? The amount of energy emitted per area per second for all wavelengths. I told you there are many wavelengths being emitted. Even my body is emitting not one wavelength. There are different wavelengths. Actually, it's a spectrum of wavelengths being emitted. And for lambda all, we have another term called total emittance. Similarly, there are two more things: spectral absorptance and total absorptance. But that is not important for you anyway. Just know that there are something else called there is something else called total emittance, spectral absorptance and total absorptance. They are similar to these two. And if you take the emissive power of total emittance of a practical body, real body, to total emittance of a black body, perfectly black body, that is called emissive power for the body. Emissive power, okay, emissive power for the body. So what is emissive power? It is E practical divided by E black body. For a perfectly black body, E practical is same as E black body, which is equal to 1, which would mean it is equal to 1. And emissivity is actually between 0 and 1. 0 and 1. Look at that. I'll repeat one more time. These are some important points that are confused. They are confusing as well, a little confusing as well. But just know the terms. That's it. Okay, this is lambda 1. I told you I've taken a body that emits radiations. This is a body that emits radiations. Okay, just imagine it is my body. Okay, I'm drawing a square here. Look at that square here. So 1 centimeter length, 1 centimeter breadth. I have square here. And from this area, how much of energy is emitted per second? So energy emitted per area per second is called what? Spectral emittance. If it is for one wavelength, only one wavelength. If you count only one wavelength, it is called spectral emittance. Spectral emittance. And what is total emittance? If you calculate this for all wavelengths, if I take the energy emitted per area per second for all wavelengths, my body emits different types of radiations, different wavelengths. Actually, radiations of different wavelengths are being emitted from my body, right? So if you take it for one wavelength, that is Q by AT is called spectral emittance or monochromatic emittance. Similar way, total emittance is nothing but energy radiated per area per second for all wavelengths, lambda for all. And then, if you take total emittance for a practical body to total emittance of a black body, perfectly black body, okay, total emittance for a real body, practical body, to total emittance for a perfectly black body, this is called emissive power of the body. Emissive power of the body. So what is emissive power? It is E practical by E black body. But for black body, both these are equal. No, perfectly black body, both these are equal. So for perfectly black body, we could say that E is equal to 1. Emissive power is equal to 1. Emissive power value ranges between 0 and 1. 0 less than E less than 1. Did you understand all these? So I'll quickly repeat this. What is spectral emittance or monochromatic emittance? This is called monochromatic. Monochromatic means single wavelength. Spectral emittance or monochromatic emittance is what? The energy emitted per area per second. From unit area, how much of energy is emitted per second. For one wavelength, for one particular wavelength, it is called spectral emittance or monochromatic emittance. And if you consider all wavelengths emitted, the energy radiated per area per second is called total emittance, lambda all, total emittance. And like I said, emissive power is the ratio of total emittance for a practical body, real body, to total emittance of a black body. And I said this value can range between 0 and 1. You must know this because it's a previous question. Emissive power can be between what and what? 0 and 1. And the maximum value for a perfect black body, emissive power is equal to 1, because these values will be equal So they'll get cut, leaving you with 1. Okay, so that is the first part. And I'm going to draw black body radiation spectrum here. This is an important thing. You know, this is how black body radiation spectrum is to be drawn. Look at this. I have drawn black body radiation spectrum. This is emissive power that I'm drawing here. Emissive power, that means the total energy emitted per area per second. Oh, tell me what was emitted? Total emittance, do you remember? Total emittance was what? Spectral emittance was for one wavelength, total emittance for all wavelengths, right? I have drawn it for all wavelengths. Look at that. Lambda, all wavelengths. I have drawn for all wavelengths. It is actually a curve. It's a curve. This is called, tell me, black body radiation curve. This is called black body radiation curve. This is called black body radiation curve. This is very, 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 very important. Radiation curve. Black body radiation curve. Okay. And this particular value is called lambda maximum. So that is the wavelength value for which you have maximum emittance, right? Right. Am I correct? I'll draw it one more time. Let us not intercept it with x-axis. Okay, so I'm drawing few of them. This is emittance here, total emittance here. I'm drawing lambda here. I told you different wavelengths are emitted. So this is one of the graphs. Okay. I'm drawing another graph here. I'm drawing another graph here. Look at this. I'm drawing another graph here, like this. You know, here lambda maximum is here. For this one, lambda maximum is here. And this one, lambda maximum is here. So lambda maximum is here. And I say that this temperature is T3, this is T2, this is T1. I have drawn it for 3 different temperatures. One black body is kept, and I have drawn 3 different graphs for 3 different temperatures. What do you understand from this? I'll tell you T3 is greater than T2, greater than T1. What do you understand from this? Lambda maximum shifts to the left. Lambda maximum shifts to the left as temperature increases, or lambda maximum decreases as temperature increases. Am I correct? This is called Wien's displacement law, one of the most important laws here. Wien's displacement law. Displacement law. Why is it called displacement law? Because the lambda maximum value displaces to the left as temperature increases. Lambda maximum decreases as temperature increases. Did you understand? I'll draw it one more time. We are drawing what? Black body radiation curve here. Black body radiation curve. Look at this. This is emittance, total emittance on y-axis. That is total energy emitted per area per second. Correct. Total emittance, not spectral emittance. Total emittance is drawn on y-axis. Total energy emitted per area per second. Okay. Total energy emitted per area per second for all wavelengths. Lambda, all wavelengths. I draw it like this. So this is where lambda m is for T1, first temperature. Okay. Lambda m. All right. I'm calling it lambda m for 1. And for next one, you know, as you can see, it is shifting to the left. Lambda m for 2. Because that temperature is T2, that temperature is a little greater. And for the next one, as you can see, it is shifting to the left. Lambda m for 3. And what do you understand here? Lambda m for 3. Lambda m for 3 is less than lambda m for 2 is less than lambda m for 1. Lambda m for 3 is closest to the origin. So that is the smallest value. Lambda m for 3 is smallest. Then comes lambda m for 2. Then comes for lambda m for 1. And what about temperatures? I told you this temperature is T3. This is T1. T3 greater than T2, greater than T1. So when the same body, this is drawn for same body at different temperatures. You take a black body and then you heat it to different temperatures. You draw the graph for energy radiations. And this is how the graph is obtained. And what do you observe from this? As you can see, lambda m is shifting to the left as temperature increases. Lambda m displaces to the left as you go, as the temperature is increased. Or lambda m is less when temperature is more. Look at that. Lambda m3 less than lambda m2 less than lambda m1. So T3 greater than T2 greater than T1. Smallest lambda m is for 3. Greatest temperature is for 3. Which means lambda m is proportional to 1 by T, or lambda m is equal to a constant into T. This constant is called Wien's constant, whose value is 2.88 into 10 power minus 3 meter Kelvin. That is the value of Wien's displacement, Wien's constant. And there are two things to be drawn. I'll draw the graph of lambda m against t. What sort of a proportionality is this? They are inversely proportional. So if I draw lambda m against temperature, the graph looks like this. Inverse proportionality, right? Inverse proportionality. Look at the graph, inversely proportional. And if I take frequency graph, what about lambda and frequency? Do you remember this nu is equal to v by lambda? They are inversely proportional, right? So I can write lambda m will be what? Lambda m will be what? I can write it as C by nu m is proportional to 1 by t. C is constant, right? So nu m is proportional to t. So if you draw the graph of nu m against t, it's a previous question, the graph will be a straight line because this is direct proportionality. Direct proportionality. Did you understand these points? We're going back to this one more time. You know, like I told you, if I draw lambda on, sorry, not lambda, total emittance on y-axis, total emittance. Total emittance means the total amount of energy emitted per area per second for all radiations, you know, and lambda on x-axis, you have a graph like this. And this is where lambda maximum is located. And if you draw it for another temperature, lambda m shifts to the left. Lambda m is shifting to the left. Look at this. And for a third one, lambda m further shifts to the left. So lambda m for 2, lambda m for 3. So I can call them lambda m1, lambda m2, lambda m3. Which is the smallest? Lambda m3. As you can see, is the smallest. That is closest to origin. Lambda m3 less than lambda m2 less than lambda m1. Temperatures are what? This is T3, this is T2, this is T1. T3 greater than T2 greater than T1. These are the temperatures. Okay. So if you look at this, it is obvious that lambda m is proportional to 1 by t. As lambda increases, t decreases. Look at, if you go to the right, lambda increases. If you go to the right, temperature decreases. So lambda m is proportional to 1 by temperature. This is very important. It is called Wien's displacement law because lambda maximum displaces to the left as temperature increases. Okay, you know, so I can put a constant here. Lambda m is equal to b by t. This is called Wien's displacement law, and b is equal to 2.88 into 10 power minus 3 meter Kelvin. Meter Kelvin is called Wien's constant. Wien's constant. And then we have a couple of graphs here. If you graph number 1, lambda m and t, lambda m and t. If I take lambda m here, t here, the graph will be a rectangular hyperbola. Why? Because lambda m is proportional to 1 by t. If we have inverse proportionality, this is inverse proportionality, the graph will be a rectangular hyperbola because when one increases, the other must decrease. Number 2, I'm going to draw frequency. Lambda and frequency are what? Lambda and frequency are what? Lambda is equal to C by nu. Do you remember? Lambda is equal to C by nu. Do you remember? So lambda m is equal to C by nu m. So I can write it here. Lambda m is equal to C by nu m. So I write it here. C by nu m is proportional to 1 by t, which means nu m. C is constant, right? This is on denominator, this is on denominator. So nu m is proportional to temperature. So if you draw nu m against temperature, the graph is directly proportional. Relation is directly proportional. So if you have direct proportionality, graph is a straight line. If you have inverse proportionality, graph is rectangular hyperbola. If you have direct proportionality, graph is a straight line. Hope you understood this now. Have you finished writing this? Someone please tell me. Okay, now I'm going to tell you one more graph here, but that is very rarely asked. In case they ask, I'll tell you this is lambda m into t is equal to b. Am I correct? I cross multiply. Correct? I take logarithm ln lambda m, logarithm of lambda m plus logarithm of t is equal to logarithm of b. Correct. So logarithm of lambda m will be what? Logarithm of b minus logarithm of t. Correct. I'll repeat one more time. This is lambda m into t is equal to b. I take logarithm on either side. You learn one thing in lower classes, logarithm of a into b is equal to what? Logarithm of a into b is equal to log a plus log b. Do you remember this? You learned this in class 7 or class 8, I don't remember. Log a into b, log a by b is log a minus log b. I'm asking everyone, what are the guys doing? Logarithm of a by b is log a minus log b. Logarithm of a into b is log a plus log b. Okay, log a plus log b. So I take logarithm everywhere. So ln lambda m plus ln lambda t. Logarithm. If I take logarithm of this, if I take ln here also I should take ln b. Right. This was lambda m into t was constant. So if I take logarithm here, this looks like log AB. Log AB is log A plus log B. So log lambda m plus log t is equal to log B. I take this to right hand side. So log B minus log t. This looks like something familiar to you. This is y is equal to c plus mx. Do you remember this equation? This equation is for a straight line. Equation is for a straight line. Can you tell me what you're going to plot on y and x axis? Can someone tell me what you're going to plot? Look at this. In place of y, what do we have? Log lambda m. So on y-axis, you should plot log lambda m. On x-axis, in place of x, you have what? ln t. ln t should be taken on x-axis. ln t is taken on, ln lambda m is taken on y-axis. ln t is taken on x-axis. Okay. And look at the slope. Slope is negative. So it's a descending graph. And then y-intercept is log b. So it should be like this. This is how the graph is drawn. Log lambda m, ln lambda m should be on y-axis. This height is actually ln b. Did you understand? So this graph is important. I told you logarithm of a into b is logarithm of a plus logarithm of b. So I take lambda into t is equal to b. This is Wien's law, Wien's displacement law. I take logarithm on either side. ln lambda m t is equal to ln b. This looks like ab. So ln ab is equal to ln a plus ln b. Correct. ln a plus ln lambda m plus ln t is equal to ln b. Right. Then logarithm of lambda m is equal to, this goes to the right side, log b minus log t. And then what? Log lambda m. This looks like y is equal to c plus mx. It is in the form of straight line. This equation is for a straight line. You have seen this many times, at least 100 times. Y is equal to c plus mx is for a straight line. So in place of y, we have lambda m, log lambda m, which means, look at this. In place of y, we have log lambda m, which means on the y-axis, you should write ln lambda m. And x-axis, in place of x, we have ln t. So ln t should be taken on x-axis. In place of x, we have ln t. And what about slope? M. M is simply minus. Minus means it is descending. Had this been positive, I would have taken upward. Okay, this is descending because slope is negative. This is called slope. Slope is what there? Slope is negative. Negative means it's coming down. It is descending graph. And then C is the constant. Y-intercept. That is where the graph starts. Look at this. This is y-intercept, this height. What is y-intercept? ln b. I have written here C is equal to ln b, this height. Did you understand that now? Now, there are two more points to be seen here. One is Stefans law. Second is Newton's law of cooling. Okay. Stefans law and Newton's law of cooling. So, first is Stefans law. Stefans law. According to Stefans law, for a perfectly black body, the amount of energy emitted per area per second, this is called total emittance, is proportional to 4th power of the absolute temperature of the body. I'll repeat one more time. According to Stefans law, this is called Stefans law. Very, very, very important. Many times questions have come from this place. This one or Newton's law of cooling, there will be a question for sure. Okay. So amount of energy emitted, amount of energy radiated. This is amount of energy radiated, Q. We've been using this notation for so long now, right? Amount of energy emitted per area. Look at this. The amount of energy emitted per area per second for a perfectly black body. Otherwise, you have to put a small letter E also, emissivity. Emissivity you don't see here because it is 1. You remember emissivity? That was 1 for a perfectly black body. Okay. Do you understand? Okay, anyway, amount of energy emitted per area per second is proportional to the fourth power of the temperature of the body, absolute temperature of the body. Or I can call this as capital letter E, hope you remember, is equal to a constant into T raised to 4. This constant is called Stefans constant. Stefans constant. Its value is sigma is equal to 5.67 into 10 power minus 8 watt per meter square per Kelvin raised to 4. It's easy to memorize. Look at this 5, 6, 7, 8. Okay, 5.67 into 10 power minus 8 watt per meter square per Kelvin raised to 4 is equal to sigma T raised to 4. And a more rigorous treatment will give you sigma into T raised to 4 minus T0 raised to 4. On rare occasions, you will have to use this equation. When atmospheric temperature is given, atmospheric temperature is given. If that is not given, first equation can be used. Okay, but watch out for the options. If such an equation option shows up, you have to choose that because this is a more precise equation. Understood? More rigorous treatment will give you the second equation. I'll repeat one more time. Stefans law. According to Stefans law, for a perfectly black body, what if it is not for a perfectly black body? There will be a knee in the equation, but don't worry about it. That is not needed at the moment. Anyway, the amount of energy radiated per area per second is directly proportional to fourth power of absolute temperature of the body. Fourth power of temperature of the body. Okay, you take the temperature of the body, take the fourth power of it. That will be directly proportional to the amount of energy radiated per area per second. Okay, so that is E is proportional to T raised to 4 or E is equal to sigma T raised to 4. Sigma value is 5.678 into 10 power minus 8 watt per meter square per Kelvin raised to 4. That is Stefans constant value. And if you take atmospheric temperature into consideration, surrounding temperature, this is body's temperature. Surrounding temperature is also given, atmospheric temperature. You have to use this equation, T raised to 4 minus T0 raised to 4. Okay. And only once it was asked like this, I will write here, sigma value, I will write somewhere here. Sigma is equal to 5.67 into 10 power minus 8 watt per meter square per Kelvin raised to 4. Okay, now this is a previous IIT JEE question. You don't have to learn this equation as such. Rate of cooling can be mathematically proved as E sigma divided by MC into T raised to 4 minus T0 raised to 4. Don't be scared looking at this equation. You know, this is not to be learned anyway. I'll tell you what to learn. There has only been one question asked on this, and that's a previous IIT JEE question. You can expect the same question in NEET examination. Okay, I'll tell you. Rate of cooling. This is actually rate of cooling. I can call it rate of cooling. Rate of cooling. Tell me, rate of cooling. Rate change in temperature per second. Oh, dt is what? Capital T stands for temperature. Small t is for time. So this is difference in temperature. This is difference in time. So change in temperature with respect to change in time. Change in temperature means what? Temperature decreases. So it is actually rate of cooling. Rate of cooling for a body. It is given by EA sigma divided by MC into T raised to 4 minus T0 raised to 4. I'll tell you the terms. E is emissivity of the body, A is area of the body, sigma is Stefans constant, M is mass of the body, C is specific heat capacity of the body, T is temperature of the body, T0 is atmospheric temperature of the body. Okay, but you don't have to learn this equation. Then why did I tell you? I'll repeat one more time. This is rate of cooling, the rate at which cooling takes place. Okay, that means the temperature decreases at what rate? The difference in temperature, difference in time. So change in temperature with respect to change in time. How much of temperature is lost in 1 second? Okay, so temperature loss in 1 second, that is called rate of cooling. Rate of cooling. I just needed to learn only one thing. E is emissivity, E is area of the body, sigma is Stefans constant, M is mass of the body, C is specific heat capacity, T is temperature, T is temperature. Temperature of the body, temperature of atmosphere. I'll tell you one thing. I can say, I told you, you don't have to learn this MC. Okay, right. But I'll tell you one thing now. Look at this. You tell me. Here, I can say R is proportional to rate of cooling. E is a constant here for a given body. Emissivity is a constant, given body, for a given body. C is a constant, specific heat capacity. Sigma is a constant. This bracket is a constant. Then only A and mass will matter. A is what? Area is 4 pi r square for a spherical body. In the previous IDJ question, sphere was asked. And mass is what? 4 by 3 pi r cube rho. Volume into density. Mass is 4 by 3 pi r cube rho. 4 by 3 constant, pi constant, rho constant. 4 constant, pi constant. Then you get rate of cooling is proportional to R square and R are 1 by R. You just need to know this. R is proportional to 1 by R. The question was to find the ratio of rates of cooling for two bodies. R is proportional to 1 by R. Understood? This is a really, really difficult question. Understood? But since you know this shortcut, it's easy now. You just have to learn this. Forget about all these things. Understood? Rate of cooling for a sphere. Okay, you don't have to learn for any other body. If they ask, they'll ask this question only. Okay, it's a previous IITJ question that has a chance of being asked again. Okay, I'll quickly repeat this part one more time. Hope this is perfectly clear. E is sigma into T raised to 4 in normal cases. And if atmospheric temperature is taken into consideration, E is equal to sigma into T raised to 4 minus T0 raised to 4. And if you modify this equation, okay, if you do a little bit of mathematics over here, you're going to get something like this. Actually, this is derived from this. Okay, they are interconvertible anyway. This is rate of cooling, dT by dt, change of temperature by change of time, is equal to E sigma by MC into T raised to 4 minus T0 raised to 4. E is emissivity, A is area, sigma is Stefans constant, M is mass of the body, C is specific capacity, T is temperature of the body, T0 is atmospheric temperature. But apart from A and M, all are constants. I can call this guy by the name rate. Rate of cooling is proportional to area on numerator. And when it was asked, sphere was asked. Sphere area is 4 pi r square. For a sphere area is 4 pi r square. Mass is what? Mass by volume is density. Cross multiply. What is mass? Mass by volume is density. So what is mass? Volume into density. 4 by 3 pi r cube is volume. Density is rho. 4 by 3 is constant. Pi constant. Rho constant. 4 constant. Pi constant. What I have is only r square on numerator and r cube on denominator. But r square gets cancelled out on numerator and denominator. And in the end, eventually you are left with r alone on denominator. So r is proportional to 1 by r. Rate of cooling is proportional to reciprocal of radius. The question was to find the ratio of rates of cooling for two bodies. I'll do the question later on. Did you understand? So we have the last point here, Newton's law of cooling. Newton's law of cooling. This is supposed to be the most important. Newton's law of cooling. According to Newton's law of cooling, dT by dt is proportional to T minus T0. Okay, dT by dt means the rate of cooling. This is rate of cooling, right? Is directly proportional to T minus T0. I'll tell you how to do this. This is an easy question. DT rate of cooling is directly proportional to T minus T0. I'll tell you the implication of this. Hot T cools down faster than cold T. Hot T. Did you hear me? Hot T cools down faster than cold T. Did you understand anything? Nothing. I'll tell you. You know, just imagine you have T at 80 degrees Celsius. T at 80 degrees Celsius. Okay, it's a really hot T. And then it cools down to 70 degrees Celsius in 1 minute. Okay, in 1 minute. Did you understand? This is hot T, 80 degrees Celsius, and it cools down to 70 degrees Celsius in 1 minute. So in 1 minute, 60 seconds, it cools down to 70. But if it needs to have the same temperature difference, when it is colder, say T is colder now, 40 degrees Celsius, and you are letting it cool down to 30, that will take what? That will take probably 3 minutes. Because when it is colder, it takes longer time for same temperature difference. Look at this. Temperature difference is same. 80 minus 70, that is 10. For the 10 degrees Celsius drop, it took around 1 minute. While for the same 10 degrees Celsius drop, it has to take 3 minutes here, 3 times as much as in the first case. Why? That is what Newton's law of cooling says. When it is colder, the cooling takes place slowly. Understood? When it is colder, the cooling takes place slowly. It's very slow. Rate of cooling is less. Rate of cooling is less. dt by dt is equal to T minus T0. I'll tell you an example question. Look at this. I'll tell you an example question. Then I have included 2 questions on the paper. We will do one by one. Okay. I'll tell you example question. You know, water cools down from 75 degrees Celsius to 65 degrees Celsius in 60 seconds. Okay. 75 to 65 in 60 seconds. All right. Calculate the time required to cool down from 45 to 35. This is the question. All right. Atmospheric temperature is given. Atmospheric temperature is 10 degrees Celsius. T0. Okay. So hope you understood this. This is Newton's law of cooling. I'll do an example question. We'll take a break. 75 degrees Celsius to 65 degrees Celsius. It cools down to 65 in 1 minute, 60 seconds. Okay. How long does it take to go from 45 to 35? 10 degree drop. Atmospheric pressure is given. This is the equation. Keep this in mind. dt by dt. I'm writing it somewhere here. This is Newton's law of cooling. dt by dt is equal to k into T minus T0. This was actually dt by dt proportional to T minus T0. But I am removing the proportionality by putting a constant. So let us write case number 1. I'm writing for case number 1. What is dt? Temperature difference. 75 minus 65. 75 minus 65. And it happens in how much time? Time is to be put 60 seconds. Is equal to k into T minus T0. What is this T? It is the average of these two. 75 plus 65 by 2 minus atmospheric temperature is 10. Did you understand how I wrote this? You know, this is the equation. dt by dt, rate of cooling, is directly proportional to difference in temperatures of body and atmosphere, surroundings. Okay. So dt by dt is proportional to T minus T0. So dt by dt is equal to constant into T minus T0. So I'm writing dt here, temperature difference. dt is temperature difference, difference in temperature. D stands for difference, difference in temperature. What is difference in temperature? 75 minus 65, 75 minus 65. By dt is the time taken for it. It is 60 seconds. 60 is equal to constant k. What is this temperature? It is the average of these two. 75 plus 65 by 2. That is how you take average. Minus, what is this T0? T0 is given. Surrounding temperature 10. So let us solve this. 75 minus 65. That is 10 by 60 is equal to k into 75 plus 65 by 2. 75 plus 5, 80. 80 plus 60, 140. 140 by 2, 70. 70 minus 10, that is 60. Let us cut this and this. You get the first equation. K1 by 6 is equal to k into 60. That is equation number 1. Similar way, let us write the second one. Second question. Second case. Tell me. Second case, you're going down from 45 to 35. So let us write down the temperature. 45 minus 35. The time taken for it is to be calculated. I knew the time for the first case, but I have to calculate the time for second case. I'm calling it T. I'm calling it by the name T. T is equal to K is same for both. Temperatures are what? 45 plus 35 by 2 minus atmospheric temperature is what? 10. Right. So tell me what you got now. 45 minus 35. 10 by T is equal to K into 45 plus 35. 45 plus 550 plus 30, 80. 80 by 2, 40. 40 minus 10, 30. So this is my equation number 2. Now I can divide equation number 1 by equation number 2. I'll have the answer. What is on the left side? 1 by 6. What is on the left side? 10 by T is equal to what is on the right side? K into 60. What is on the right side? K into 30. K gets cut, 30, 62. So take the reciprocal. I write it here. T goes to numerator, 6 comes to denominator. T by 6 and 10 together, 60 is equal to, on the right side you got only 2. Cross multiply, T will be 2 into 60, 120 seconds. Look at that. For the temperature difference of 10 degrees Celsius, there it took 60 seconds, while here it takes 120 seconds, double the same time. Did you understand? You can write this down as an example question. I'll quickly repeat this one more time. You know, the question is this: 75 degrees Celsius to 65 degrees Celsius drop takes 60 seconds. How long will it take for 45 degrees Celsius to 35 degrees Celsius? So we have the equation here, dt by dt. This is Newton's law of cooling equation, K into T minus T0. Okay, K into T minus T0. And you have used this equation here for the first case. 75 and 65 are the temperatures. So temperature dt is temperature difference. 75 minus 65 divided by dt is time. Time is 60 seconds here. Okay, and then K into this temperature is what? Average of these two. 75 plus 65 by 2 minus T0 is what? Atmospheric temperature, it is 10. Solve it, you will get 10 by 60 is equal to K into 60. I have one equation there. Do the same thing for second one. Second case is 45 to 35. So 45 minus 35 dt divided by time taken for it. It is T. I'm calculating it. The question is to calculate it, right? It's equal to K is same. Here, this temperature is average of these two. 45 plus 35 by 2 minus 10. Solve it. You get 10 by T is equal to K into 30. Then divide equation number 1 by equation number 2. Solve it. You will get only the only unknown there. T is 120 seconds. Is that clear now? Take the paper now. We will start from question number 9. We did till question number 8. We will start from question number 9. The only possibility of heat flow. Question number 9. The only possibility of heat flow in a thermoflask is through a cork which is 75 centimeter square in area and 5 centimeter square, 5 centimeter thick. Its thermal conductivity is 0.0075 calorie per centimeter per second degree Celsius. The outside temperature is 40 and the latent heat of ice is 80 calorie per gram. Time taken by 500 grams of ice at 0 degrees Celsius in the flask to melt into water at ice. So we have a thermoflask here. Look at this. This is a thermoflask. Flask, normal flask, you know, thermoflask. I'm just taking a thermal flask here. Look at this. We have a thermal flask here. And then what? And then what do they say here? Thermal flask here. All right. The only possibility of heat flow, in a thermoflask is through its cork, which is 75 centimeter square in area. So area is given 75 centimeter square and 5 centimeter thick. Length L is given 5 centimeter. Yesterday I told you, you have to take the thickness as L. Hope you remember. Conductivity. And thermal conductivity is 0.0075. Thermal conductivity is 0.0075. Okay. Then outside temperature is 40 and latent heat of fusion is 80 calorie per gram. Outside temperature is temperature outside is 80, temperature inside is 0. How do I know temperature inside is 0? Because it is ice inside. There is ice kept inside. Okay, ice kept inside like this. Ice kept inside. Okay. And then time taken by 500 grams of ice. So mass of ice is also given 500 grams of ice to melt into water at 0 degrees Celsius. Hope you got an idea now. Look at this. What is the situation here? We have I'll interpret the question here. We have a flask here, thermoflask. And thermoflask side walls are insulated. Side walls are insulated. Even the bottom is insulated. Okay. The only possibility of heat flow is through cork only, the shaded cork. Am I correct? Heat cannot flow through the walls. Heat cannot flow through the bottom either. Why? Outside temperature is 40. Okay, fine. Thank you. Outside temperature is 40. Thank you. Thanks for that. Okay. So we have a thermoflask here. Like I said, this is thermoflask. Okay. I have a thermoflask here. The bottom, you know, heat cannot come out of the bottom. Heat cannot flow through the side walls either. Because this is an insulator, heat insulator. This is heat insulator. Only heat flow is possible only through the top cork. Okay. So this is the only area through which heat can escape. Okay. So actually heat is not escaping. Heat is coming into the flask here. Why? Because inside it is ice. No, that is a lower temperature. Okay. Heat is coming in through the cork only. And tell me what? You know, heat is coming in through the cork and it is melting ice. So I can write the heat transported per second. What is heat transported per second? Heat transported per second, do you remember? K into A into TH minus TC divided by L. Yesterday we learned this. The heat transported per second is there anything regarding time? Have they given anything? How much of heat? Time taken is to be calculated. Yes, time taken is to be calculated. So K into A into TH minus TC divided by L. So I can take cross multiplication here. Q will be what? K A into TH minus TC divided by L, the whole of this into T. This is Q, equation number 1. But Q is also given by MLF. We learned the other day, MLF. M into latent heat of fusion. Now, this heat, which is transported through the cork, is used to melt ice into water. Okay. Melting ice means what? The heat required is MLF. I can obviously equate these two. This is a repeated question. Okay. Now it's very easy. All are given. You can substitute and find out time. I'll tell you one more time. Look at this. Mass, this is a thermoflask. And thermoflask has all its walls insulated. This wall is insulated. This bottom is also insulated. Heat cannot enter through the sides. Heat cannot enter through sides. Heat cannot enter through bottom either. Heat can enter through the top cork only. So heat is entering through the top cork and then it is melting ice. What is the equation for heat transported? Q by T is equal to K into A into TH minus TC over L. Yesterday we learned. And then if you cross multiply, you get Q is equal to K into A into TH minus TC over L into T. Okay, so that is equation number 1. Now this heat is used for what? This heat is used for melting ice inside. What is the heat required for melting ice? Q is equal to MLF. Heat required for melting ice is Q is equal to MLF. So you can equate these two. And if you equate these two, what we get? MLF is equal to K into A into TH minus TC, T hot minus T cold, TH minus TC into T divided by L. So let us put the values. All are in CGS. So I can keep everything in CGS. I don't have to convert anything. Mass is given as 500 grams. And latent heat of fusion is given as 80 latent heat. Thermal conductivity 0.0075 into area. Area is 75 centimeters square into temperature difference. Temperature difference is what? Outside temperature is 40, inside is 0. So 40 minus 0 into T divided by thickness is what? L, 5 centimeters, 5. So if you solve this, you will get the final answer. I'm leaving the calculation to you. I'll tell you the final answer because I don't have time. Okay. So you will get, in the end, you will get 2.47 hours. You will get this in seconds. And what you're getting is 8,900 seconds roughly. And if you convert this to hours, it is for 2.47 hours. Answer is option A. Did you understand? So question number 10. Ice starts forming in a lake with water at 0 degrees Celsius when the atmospheric temperature is minus 10 degrees Celsius. Time taken for 1 centimeter ice to be 7 hours. Time taken for 1 centimeter ice. 1 centimeter ice means what? Time taken to go from 0 centimeter to 1 centimeter is 7 hours. They are asking you to find what? What is the time taken for the thickness to grow from 1 centimeter to 2 centimeters? 1 centimeter to 2 centimeters, how much is the time? So how do we take it? Do you remember? Read the question again. Question number 10. Ice starts forming in a lake. Ice starts forming in a lake due to anomalous expansion of water. Hope you remember. Ice starts forming on a lake surface with water at 0 degrees Celsius and when temperature of atmosphere is minus 10. That is not required. If time taken for 1 centimeter ice to become 1 centimeter, that means initially there was no ice, lake was all water, and ice started forming. And when it grew to 1 centimeter, it took around 7 hours. Then the time taken for thickness of ice to change from 1 centimeter to 2 centimeters is. So 0 to 1 it takes 7 hours. 1 to 2 is how much? So what is the equation you have? T1 is equal to K into y2 square minus y1 square, correct? T2 is equal to K into y3 square minus y2 square. Okay, that is what we wrote. Then take the ratio. T1 by T2. Previous question. If you take the ratio, K's are getting cut. Y2 square minus Y1 square by Y3 square minus Y2 square. Do you remember this equation? I wrote this earlier. Hope you remember. Time taken to grow from Y1 to Y2 is T1, Y2 to Y3 is T2. So these are the equations. T1 is equal to K into Y1, Y2 square minus Y1 square, T2 is equal to K into Y3 square minus Y2 square. Then you divide, you're getting this. So tell me, T1 by T2, first time I can put 7. First time is 7. Second time is to be calculated, is equal to 1 square minus 0 square divided by 2 square minus 1 square. Look at that. Y1, Y2 square. This is Y1, this is Y2, this is Y3, this is Y4. So Y2 square minus Y1 square. Y2 square minus Y1 square. 1 square minus 0 square. This is 2 square, Y3 square minus Y2 square. 2 square minus 1 square. So 7 by T2 is equal to 1 square minus 0 square. 0 square is 0 itself. Y2 square is 4. 4 minus 1 is 3. Cross multiply T2 is equal to 7 times 3. That is 21 hours. 21 hours is there in the options. 21. 7 hours, 14 hours, less than 7 hours, more than 7 hours. Answer is option D. Answer is option D. For question number 10, answer is option D. Moving on to question number 11. Hope you finished this. Or you can take a screenshot. Question number 11. Moving to question number 11. The plots of intensity versus wavelength for 3 black bodies at temperatures T1, T2, T3 are given. It's a previous IIT JEE question. There are 3 graphs drawn. Draw the graph. Lambda drawn over here and it is intensity or E drawn here. Okay. Or I, whatever it is. And there are 3 graphs. One like this, one like this, and then one like this. Okay. There are 3 graphs. This is T1 temperature. This is T2 temperature. This is T3. Be very careful. This is T3. This is T2. Yes, T1, T3, T2. All right. And if you come here, this is lambda 1. This is lambda. Tell me. Lambda 3 and lambda 3 maximum. This is lambda 2 maximum. All right. Do you remember this? I just, we are on question number 11. Plots of intensity. Intensity means C or I, whatever you call it. Energy radiated per area per second. Energy radiated per area per second. That's also called intensity. Energy radiated per area per second. Okay. It is drawn like this. I have drawn 3 graphs here. T1, T2, T3 are the temperatures. The temperatures are such that, can you tell me the order? Now, T1, this is T1. They have said this is T1. So this is lambda 1. Wavelength maximum for the first curve. Wavelength maximum for the second curve, which is lambda 3. Because it is T3. For the thermal, it is lambda 2. And from the figure, it is clear that lambda 1 is less than lambda 3, which is less than lambda 2. Who is the closest? Lambda 1, closest to the origin. Then lambda 3, then lambda 2, lambda 1 less than lambda 3 less than lambda 2. So temperatures will be in the reverse order. Do you remember Wheel's displacement law? Do you remember lambda ms proportional to 1 by t? Greater the value of lambda, lesser is t and vice versa. So T1 greater than T3 greater than T2. So correct option is what? Answer is option T1 greater than T3 greater than T2. Answer is option B. Second option is correct. Second option is correct. Option B is correct. Option B is correct. Question number 12, I'll come back and do. That's a previous question. Question number 12, I'll come back and do because I forgot to tell you that concept. 13, 14, 15 we'll do. 13th question. Height also may change. Height also may change. It doesn't matter. Okay. Lambda maximum, you have to take wavelength corresponding to maximum. That's it. Question number 12, we'll come back and do. Question number 13. The energy spectrum of a black body. Question number 13. 12 we will do later. Question number 13. The energy spectrum of a black body exhibits maximum wavelength, maximum around wavelength lambda 0. So lambda 1 is lambda 0. All right. The temperature of black body is now changed such that the energy maximum around the wavelength is 3 lambda 0 by 4. Lambda 2 is 3 lambda 0 by 4. So temperature is T1 here, temperature is T2 here. Okay. Temperature is T1, temperature is T2. Read it again. Question number If you have any questions, you can type it in here. Okay, I'll see. The energy spectrum of a black body. Question number 13. The energy spectrum of a black body exhibits a maximum around wavelength lambda 0. So lambda 1, first case lambda is lambda 0. The temperature of the black body is now changed such that energy is maximum around 3 lambda 0 by 4. Second lambda is 3 lambda 0 by 4. Second maximum is 3 lambda 0 divided by 4. Okay, and that happens at another temperature, right? The power radiated by the black body will now increase by a factor of energy radiated. They are talking about energy radiated, right? Power radiated or energy radiated. I'll tell you. What do we say about this? Lambda m into t is equal to a constant. Correct. Which means lambda 1 t1 is equal to lambda 2 t2. Lambda into t is equal to constant. This is what Wien's displacement law says, right? Lambda into the product of lambda and t are constants. Correct. Is a constant. Lambda and t is a constant. The product of lambda and t is a constant. So lambda 1 t1 is equal to lambda 2 t2. Lambda 1 t1 is equal to lambda 2 t2 is equal to lambda 3 t3 is equal to lambda 4 t4. It goes on like that, right? So lambda 1 is t1. Lambda 1 is lambda 0 into t1 is equal to. Second case lambda is 3 lambda 0 by 4 into t2. I can cut this tc lambda 0. What is t1 by t2 then? T1 by t2 is 3 by 4. I got t1 by t2. Is that the question? Are you required to find ratio of temperatures? No. Power radiated. Power radiated, you know. Power radiated is actually obtained from E is equal to sigma t raised to 4. This is actually power. That's also called power. Energy radiated per area per second. That's also called power. Okay, energy radiated per second. Okay, so this is actually what? Q by AT. What I need is power. So Q by T is power, right? It's equal to A sigma T raised to 4. So if I want to take the ratio of P1 to P2, it is T1 raised to 4 by T2 raised to 4. Why? Because A is constant, sigma is constant, same body, right? T1 raised to 4 by T2 raised. So T1 by T2 raised to 4, which is what? 3 by 4 raised to 4. 3 into 3 into 3 into 3. 81 by 4 into 4 into 4 into 4. 4 into 4, 16. 16 into 4, 64. 256. So P1 by P2. P1 by P2 is 256 by 81. So P2 will be what? P2 will be cross multiply. 256 divided by 81 into P1. Do you see any such options here? 256 by 81. Answer is option A. I'll explain this one more time. What is given in the question? The energy spectrum of a black body exhibits maximum around a wavelength lambda 0. So first case maximum is lambda 0. Temperature I can call T1. The temperature of black body is now changed. So another temperature T2, such that the maximum falls around wavelength 3 lambda 0 by 4. So maximum is 3 lambda 0 by 4. Power radiated is to be calculated. Will increase by a factor of. So first of all, we have this equation. Lambda and T are given. No. Lambda is given, T is given. So you must think on those lines. Lambda and T are related by which equation? Lambda and T are related by which equation? Wien's displacement law. Am I correct? Tell me. It's a multi-concept question. You have to use both Wien's law and Stefans law. Okay. So first of all, how do you arrive at this conclusion? Because you see lambda there, you see T mentioned there, T being mentioned there. So you must relate them. What is the relation connecting lambda and T? Lambda into T is equal to constant, which means lambda 1 T1 is equal to lambda 2 T2, is equal to lambda 3 T3, is equal to lambda 4 T4. So lambda 1 T1 is equal to lambda 2 T2. Lambda 1 is lambda 0. T1 is T1. Lambda 2 is 3 lambda 0 by 4 into T2. So T1 by T2 will be what? 3 by 4. I got T1 by T2. But the question is to find out power radiated. What is power? I have an equation for Stefans law. Stefans law says what? E is equal to sigma T raised to 4. E means Q by AT. Energy radiated per area per second is sigma T raised to 4. I take A to the right hand side. A is taken to the right hand side. A sigma T raised to 4 is Q by T. Energy by time is called power. Class 9. We learned this in class 9. Power is equal to energy by time. A sigma T raised to 4. So for two bodies, if I write, P1 will be what? A sigma T1 raised to 4. P2 will be what? A sigma T2 raised to 4. A is same for both. Sigma is same for both. Same body, right? Same body. So if you cut them, if you find the ratio P1 by P2, T1 by T2 to the whole raised to 4. T1 by T2 means 3 by 4. T1 by T2 is 3 by 4 here. 3 by 4 the whole raised to 4. 3 raised to 4 is 3 into 3 into 3 into 3. 3 into 3, 9. 327. 381 by 4 into 4, 64. Into 4, 4 into 4, 16. Into 4, 64. Into 4, 256. So B1 by B2 is 256. Or 81 over 256. Cross multiply. P2 will be what? 256 comes here. 81 comes here. 256 by 81P. So the question is to find by what factor. So it is 256 by 81. Answer is option A. Answer is option A. Did you understand this? Question number 14 is also a little complicated. Let's keep it there. It's a previous IDG question. We'll come back and do. So there are two questions to be done there, 12 and 14. 15 onwards, we'll quickly do them and then come back and do this. Question number 15. Which of the following is nu mt graph for a perfectly black body? You remember nu m and t. Do you remember lambda m against t graph? This is how it looks like. Lambda m here, t here. The graph is a rectangular hyperbola. Nu m against t graph, nu m and t. Nu m is here and t here. You get a graph like this is a straight line. And then log lambda m against log t graph. Do you remember the graph? Log lambda, ln lambda, ln t. This is how the graph would look like. All these graphs are important in what you call Wien's displacement law. So which of the following is nu mt graph? Nu mt graph. Nu mt graph is this. So this graph, no, it should be a graph with positive slope and starting with 0 intercept. So answer is option B. Second graph is correct. A, B, C, D graphs are there, out of which B is correct. Okay. Question number 16. Answer is B. For question number 15, answer is B. 16 to 20, very quickly. Two black metallic spheres of radii 4 meters at 2000 Kelvin and 1 meter at 4000 Kelvin will have the energy radiation as two black metallic spheres. Radius is what? Radius 4 meters. So first one's radius is what? Radius of the first one is 4 meters. And then temperature of first one. Temperature of first one is 2000 Kelvin. 2000 Kelvin. Right. We are on question number 16 now. Radius of second one. Radius of second one is how much? It is 1 meter. And temperature of second one is 4000 Kelvin. 4000 Kelvin. Okay. Read it again. Two black metallic spheres. There are two black metallic spheres. Radius 4 meters. Radius 4 meters. Temperature 2000 Kelvin. Temperature 2000 Kelvin. Second one, radius 1 meter. Temperature 4000 Kelvin. Energy radiation ratio. Energy radiation. Again, temperature is mentioned. So which is the equation? E is equal to sigma T raised to 4. Energy radiation is to be calculated. This is Q by AT, right? Is equal to sigma T raised to 4. They are asking you to find energy. Q is equal to sigma A T raised to 4 into T. Okay, so Q1 I can write sigma 4 pi R1 square T1 raised to 4 into T. Why? Nothing. I've just written this equation. I've just modified this equation. Q is sigma, sigma. Area of a sphere is 4 pi R square. Area of a sphere is 4 pi R square. Then T, T1 raised to 4. Small t, small t. Second case, Q2. Sigma 4 pi R2 square T2 raised to 4 into T. Same time, no? Over same time you have to calculate. And they're asking you to find the ratio of these Q1 to Q2. If you divide sigma 4 pi T cut R1 square by R2 square into T1 by T2. T1 raised to 4 by T2 raised to 4. Tell me what you get. R1 square by R2 square. R1 square. 4 square by R2 square. 1 square into T1 by T2. T1 is 2000 by T2 is 4000 raised to 4. 3 zeros are cut. 3 zeros are cut. So 4 square is 16 into 16 by 1 is 16. 2 raised to 4. 2 into 2. Oh, 2 and 4 are cut. It is 2. 1 by 2 raised to 4. It is 1 by 16. Answer is 1:1. Is that there in the options? 1:1. Option A. Option A. I'll repeat this one more time. Look at this. What is the question? There are two spheres they have given. Previous All India question. Two spheres given. Radii are what? Radius of the first sphere is 4 meters. Radius of the second sphere is 1 meter. Temperature of the first sphere is 2000 Kelvin. Temperature of the second sphere is 4000 Kelvin. They are asking you to find the ratio of energy radiation. Energy radiation. Okay. So energy radiation means E is the equation. E is equal to sigma T raised to 4. You have to use what? You have to use Stefans Law. So E is what? Q by AT. Energy per area per second. I've told you a billion times now. Then cross multiply. Q will be equal to sigma AT raised to 4 into T. What I need is energy radiation. So Q1, first case. Sigma into area is 4 pi r square. For a sphere, the total area is 4 pi r square into T1 raised to 4 into T. And Q2 is sigma is same for both. 4 pi r2 square into T2 raised to 4 into T. When you divide Q1 by Q2 is R1 square by R2 square. Everything else get cut. You know, T R1 square by R2 square into T1 by T to the whole raised to 4. So if you put the values, R1 is 4, R2 is 1, and then T1 is 4000, 2000, T2 is 4000. Then 2000 and 4000 are cut, you are getting 2 on denominator. Then 4 square is 16, 1 square is 1, 16 into, this is 1 by 2 raised to 4, 1 by 2 into 1 by 2 into 1 by 2 into 1 by 2, that is 1 by 16. 16s are cut, you're getting 1:1. Answer is option A. Let us look at question number 17. Let's make it very quick. 17th question. 17th question. 17, 18, 19, 20. We'll finish them in 10 minutes. Okay. 17th question. Two metallics. Oh, question number 17. Two identical metal balls at temperatures 200 and 400 Kelvin degrees Celsius kept in air at 27 degrees Celsius. Yes, temperatures are given. T1 is equal to 200. 200 plus 273, that is equal to 473 Kelvin. Everything has to be kept in Kelvin. All right, everything has to be kept in SI. So all have to be kept in Kelvin. So T1 is equal to 200 Kelvin. T2 is what? How much is the second temperature? 400 plus 273. That makes it 673 Kelvin. So what all are given? Read it again. Two identical metal balls at temperatures 200 degrees Celsius and 400 degrees Celsius. So temperature 1 is 200 plus 273 to convert to Kelvin. That is 473 Kelvin. Then second temperature 400 plus 273. That makes it 673 Kelvin. Okay, kept in air at atmospheric temperature is also given. T0 27 plus 273. That is 300 Kelvin. Atmospheric temperature is given. Now be very careful. Ratio of heat loss by these bodies is ratio of heat loss. Do you remember? Energy is given by, since atmospheric temperature is given, you must take this equation for Stefans law. Do you remember? Oh, I had told you. Energy, Stefans law is given by what? Energy radiated per area per second. Energy radiated per area per second, which is capital letter E, is equal to sigma T raised to 4 in normal conditions. But here, they have specifically given the atmospheric temperature. So atmospheric temperature is given. Look at that. So I have to take that into consideration. So this is the true equation to be used. So I can write E1 is equal to sigma into, first case, T1 raised to 4, 473 raised to 4 minus T0, 300 raised to 4. And E2 is equal to sigma into second temperature, 673 raised to 4 minus 300 raised to 4. And you've been asked to find the ratio here, E1 by E2. The sigma and sigma are cut. Answer is 473 raised to 4 minus 300 raised to 4 divided by 673 raised to 4 minus 300 raised to 4. In such questions, you know, they never expect you to solve this. You can keep it in this form. There should be a correct option like this. That looks like this. Answer is option D. 473 raised to 4 minus 300 raised to 4 divided by 673 raised to 4 minus 300 raised to 4. Why did I use this equation itself? Because they have particularly given you the atmospheric temperature. So you must take an equation that involves atmospheric temperature. Is that clear? Question number 18 is a previous IIT JEE question, and that is the only question based on this equation till date, asked till date. Question number 18, two metallic spheres S1 and S2. Two metallic spheres S1 and S2 are made of same material and have same identical surface finish. That means they have both same emissivity. E1 is equal to E2. They are made up of same material. and same identical finish. The mass of S1 is 3 times that of S2. Mass of S1 is 3 times that of S2. Okay, mass of first one is 3 times that of S2. Look at that again. There are two spheres. There are two spheres. One sphere here, second sphere here. Then what else? They are made up of same material and identical surface finish. Identical surface finish means they have same emissivity. E1 is equal to E2. Don't worry about it. So this question alone will be asked. The mass. The mass of S1 is 3 times that of S2. Mass of S1. First one's mass is 3 times that of S2. Both the spheres are heated to same high temperature and placed in same room having same temperature. T1 is same for both. T0 same for both. Okay. T is same for both. T is same for both. They are heated to same temperature. They are kept in same room. So whatever it is, the ratio of initial rate of cooling of S1 to S2 is initial rate of cooling. Do you remember rate of cooling equation? dt by dt is equal to EA sigma divided by MC into T raised to 4 minus T0 raised to 4. Do you remember this? This is the equation for initial rate of cooling. I told you initial rate of cooling is EA sigma. Hope you remember this. I had told you EA sigma by MC into T raised to 4 minus T0 raised to 4. Both are having same surface finish. That means E is same for both. Sigma, Stefans constant, same for both. Both are of same material, means C is same for both. Same temperature, they say. They are brought to same temperature. Understood? They are raised to same temperature. So T is same for both. They are kept in the same room. Room temperature is also same. So that is dependent on A and M only. And we have proved that R is proportional to 1 by R. Hope you remember this. So what is R? 1 by R2 then? Rate of cooling of first one to second one. Inverse ratio. That is R2 divided by R1. Radii. Inverse ratio. I'm going to find this. I can put it here. What is mass of S1? 4 by 3 pi R1 cube rho is equal to 3 times. What is mass of second one? 4 by 3 pi R2 cube rho. So 4 by 3 pi rho. R1 cube is equal to 3 times R2 cube. So what is R2 cube by R1 cube? 3 is taken to left, 1 by 3. So what is R2 by R1? Cube root of it, 1 by 3 raised to 1 by 3. So R2 by R1 is to be is needed here. R2 by R1 is what? 1 by 3 raised to 1 by 3. Do you see that in the options? Actually, it's a very lengthy and tough question. 1 by 3 raised to 1 by 3, answer is option B. But this shortcut makes it very simple for us. Rate of cooling, I'll repeat this. Initial rate of cooling is given by dt by dt is equal to EA sigma by MC into T raised to 4 minus T0 raised to 4. But they say in the question that they are of identical finish. Surface finish is same for both. That means emissivity will be same for both. Stefans constant is same for both. That's it. That is understood. Then specific heat capacity is same because they are made up of same material. And they say that temperature up to which they are raised is same. T is same. Atmospheric temperature, they are kept in same room. So that is also same. So A and M alone matter. So rate of cooling is, we have proved this equation 1 by R. So they are inversely proportional. So R1 by R2 will be R2 by R1. Rate of cooling of first one to rate of cooling of second one is equal to radius of second one to radius of first one. They are in the inverse ratio. So I need to find R2 by R1 ratio. How do I find it? I've been given the ratio of masses. M1 to M2. M1 is what? Mass is volume into density. Oh, tell me what? Mass by volume is density. So cross multiply. Mass is equal to volume into density. So for this mass, I can write volume into density. 4 by 3 pi R1 cube into rho. Right side, 3 is there, 3 is there. Look at that. Into 4 by 3 pi R2 cube rho. Then rho cut. Rows are identical because made up of same material. 4 by 3 pi cut. In the end, you are left with R1 cube on left side, R1 cube. 3 R2 cube on right side, 3 R2 cube. What I need is R2 by R1 here. So I'll take R1 cube to the right side. R2 cube by R1 cube is 3 goes to the left, 1 by 3. This is R2 by R1 the whole cube. R2 by R1 the whole cube. What I want is R2 by R1 only. So I need to take cube root. When I take cube root, it is R2 by R1 on right side. This is 1 by 3's cube root. 1 by 3 raised to 1 by 3. So answer is 1 by 3 raised to 1 by 3. Answer is option B. Did you understand this? Question number 19 and 20 are based on Newton's law of cooling. Question number 19. A cup of tea cools down from 80 to 60 in 1 minute. So 80 degree to 60 degree in 1 minute. 1 minute means 60 seconds. A cup of water, a cup of tea. Question number 19. A cup of tea cools down from 80 to 60 in 1 minute. 1 minute means 60 seconds. The ambient temperature is 30 degrees Celsius. Ambient temperature means atmospheric temperature. It is 30 degrees Celsius. In cooling from 60 to 50, it will take how much time? 60 to 50. 60 to 50 is asked. 60 degree to 50 degree, how much is the time taken? T is how much? You know how to do this, right? You remember the equation dt by dt. This is the basic equation. dt by dt is equal to k into t minus t0. K into t minus t0. Correct. So let us put dt, first case, 80 minus 60 divided by time taken for it. Time taken is 60 is equal to constant into what is this T? That is average of these two temperatures. 80 plus 60, 140. Okay, I'll put it here. 80 plus 60 divided by 2 minus ambient temperature is 30. So I'll simplify this. 80 minus 60 is 20. 20 by 60, 1 by 3. Look at that. 80 minus 60, 80 minus 60, that is 20. 20 by 60 is 1 by 3. 20 and 60 are cut, you get 1 by 3. K into, what is this? 80 plus 60, 140. 140 divided by 2, 70. 70 minus 30 is 40. So I get my first equation. Now, second one I can do here, dt by dt, say the temperatures are 60 and 50 there, 60 and 50. So 60 minus 50 divided by the time needed for it, which is to be calculated, is equal to K into, what is average of those? 60 plus 50 divided by 2 minus ambient temperature is 30. Ambient temperature is 30. Okay. So this is 60 minus 50 is 10 divided by T is equal to K into 60 plus 50, 150. Sorry, 110. 110 by 2 is 55. 55 minus 30 is 25. Equation number 2. Then divide these two. 1 by 3 by 110 by T. 1 by 3 by 10 by T is equal to, right side K cut, 40 by 25. Take left numerator. Take this numerator. So T divided by T goes to numerator and 3 goes along with 10. It is T by 30 is equal to 40 and 25 cut with 5. It is 8 by 5. 8 by 5. 5 and this are cut. This is 6. Cross multiply 6 into 8 is 48 seconds. Is it there in the options? 48 seconds. Answer is not there. Option D is the closest one, but such a question will be removed. Don't worry, answer is 48 seconds. Did you understand? Right. Let us look at question number 20. A body takes how many minutes? T minutes. A body takes T minutes to cool from 62 to 61. So a body takes T minutes, capital T minutes, 62 to 61. So 62 degrees Celsius to 61 degrees Celsius, it takes T minutes. When the surrounding temperature is 30. Surrounding temperature is what? Ambient temperature is 30. A body takes capital T minutes to cool down from 62 to 61. The time taken by the body to cool from 46 to 45.5. 46 to 45.5. By all chances we may go wrong. That is why I've included this question as well. Okay, you have to find the time there. Okay, equal to T seconds, greater than T minutes, less than T minutes, equal to T by 2 minutes. So let us see the questions now. Question now. Okay, what is the first one? I told you 62 minus 61. 62 minus 61 dt divided by time taken for it is T is equal to K into average of these two, 62 and 61. 62 plus 61 by 2. It is 61.5. How do we take it? Take the difference between them, that is 1. And that is to be equally split up, 0.5, 0.5. Add 0.5 with this. Subtract 0.5 from this. You get 61.5, right? Minus ambient temperature is 30. So it is what? 62 minus 61. 1 by T is equal to K into, this is 31.5. I got answer to first part. No, I got the first equation, right? T1 by T. Second case, I can write 46 and 45.5, right? 46 minus 45.5 divided by time taken for it is t is equal to k into average of these two, 46 and 45.5. Average of them is what? Average of these is what? Find the difference, 0.5. Split it into half, 0.25. Add it with a smaller quantity. So average is 45.75. Or you calculate it yourself. 45.75 minus ambient temperature is 30. 46 minus 45.5, that is 0.5. Divided by T is equal to K into 45.75 minus 30 is 15.75. Question number 2. Then let us divide this. On the left side, 1 by T. On the left side, 0.5 by T. Okay. Is equal to, on the right side, K into 31.5. On the right side, K into 15.75. K and K are cut. This and this are cut. It is 2. Okay. Cross multiply. This T goes numerator. T divided by 0.5 into T is equal to 2. Cross multiply, small t is equal to 2 into 0.5 T. That is capital T. So answer is equal to T minutes. Small t is equal to T minutes. Answer is option B. Option B. Look at that. 62 to 61. 1 degree difference takes T minutes. 46 to 45.5. Only half degree. That also would take T minutes. Did you understand these questions? There are 2 more questions remaining apart from the 3 homeworks that I gave in the last class. Homeworks remain homework. I'll send the solutions after the class. For these questions, I'll tell you the solution. Question number 12, the adjoining diagram. Question number 12, the adjoining diagram shows the spectral densities. Adjoining diagram shows the spectral densities, spectral energy density of E lambda of a black body at 2 different temperatures. The area under the curves are in the ratio. Area under the curves are in the ratio 16:1. The value of temperature is, you've been given 2 graphs here. Look at the graphs. This is E lambda. I've taken E here and lambda is taken here. There are 2 graphs drawn. One graph like this, that is at T Kelvin. Another graph is like this, that is at 2000 Kelvin. Okay, 2000 Kelvin. So 2000 Kelvin, and then what is given? Areas under the curve. Areas under the curve. So T1, I can take A1 as I can take T1 as temperature T Kelvin, then T2 is equal to 2000 Kelvin, and A1 by A2 ratio is 16:1. Okay, read it again. Question number 12. The adjoining diagram shows spectral energy density distribution. Black body energy distribution. Black body radiation curve. We learned it before. Of at two different temperatures, T1 and T2. One is T1. This is T1. Okay, this is T1. This is T2. Okay, and their areas are in the ratio. Areas of the curve. Area. Look at this area of this curve and area of this curve are in the ratio what? Areas are in the ratio 16:1. Bigger area by smaller area. A1 by A2. I can't take A2 by A1 because 1 is given for the bigger curve. Look at that. 1 is the number for bigger curve and 2 is for smaller curve. Look at that. T2. So A1 by A2 is 16. Bigger one by smaller one. I forgot to tell you area of this curve is actually E. We have to write this as a noun. Area under the curve. Area under the curve is actually E. And what is the relation you learn? E is proportional to T raised to 4 Stefans Law. So E1 by E2 will be what? E1 by E2 will be T1 by T2 the whole raised to 4. Correct? E1 by E2 is same as area 1 by area 2 is T1 by T2 the whole raised to 4. So if you solve this A1 by A2, it is there. It is 16 is equal to T1 by T2, T divided by 2000 raised to 4. So if you simplify this, T by 2000 raised to 4, if you simplify this, what do we get? So, the options are, you can take fourth root, 2 into 2 into 2 into 2, that is 16. So fourth root would be 2. This is like 2 by 2000 cross multiply. T will be 4000 Kelvin. Is that there? Answer is option D. I'll repeat one more time. Before going to this question, you need to know one thing. This is to be written as important note. Okay, area under E lambda curve, area under E lambda curve, area under black body radiation curve, area under the curve. Look at the shaded area. I've shaded the area, no? Area under the curve is actually energy density. This is energy per area per second. Don't you remember? Energy radiated per area per second. Area under the graph is energy radiated per area per second. And it is given what? First temperature, the bigger one's temperature is T Kelvin, and second one's temperature is 2000 Kelvin. And then A1 by A2 ratio is also given, that is 16 by 1. You can't take A2 by A1 because bigger one is number 1. So that's its area should be equal to A1 because bigger area should be A1. Numerator is greater, right? A1 should be greater than A1 by A2 is 16. So E is proportional to T raised to 4 is our equation. E1 by E2 will be T1 by T to the whole raised to 4. So E1 is what? E1 by E2 same as what? E1 by E2, I told you, no, E is, where is it? E is area, right? E is area, right? E is area, right? So E1 by E2 can be written as A1 by A2. E is area. So E1 is area 1, E2 is area 2, E1 by E2 is A1 by A2, is T1 by T to the whole raised to 4. A1 by A2 is given in the question as 16, then T1 is T in the question, T2 is 2000 in the question, then raised to 4. I take 4th root on either side. So when I take 4th root here, 2 into 2 into 2 into 2 is 16. So 4th root is 2. There, if you take 4th root, that will be gone. T by 2000 cross multiply, that will be 4000. Answer is option D. Did you understand? Question number 14 is a previous IIT question. A black body is at a temperature of 2880 Kelvin. Black body is at a temperature of 2880 Kelvin. The energy radiation emitted by this object with the wavelength between 499 and 500 is U1, 999 and 1000 is U2, and 999,000 is U2, and between 1499 and 1500 is U3. Okay, so we have a black body radiation here. Look at this black body radiation spectrum, which I can draw E lambda. This is the black body radiation spectrum. What is given? Black body temperature is at a temperature 2880. The energy radiation emitted by this object with the wavelength between 499 and 500. 499 and 500 is, it is U1. Okay, 499 nanometer and 500 nanometer, it is U1. Between 999 nanometer and 1000 nanometer, it is emission is U2. Energy is U2. Between 1499 and 1500, it is U3. Okay, then Wien's constant is given. Then U1 is equal to 0, U3 is equal to 0, U1 greater than U2, U2 greater than U1. I'll tell you what. Look at this. You know, I've been given temperature here, and it's about lambda. So I can use what? Wien's displacement law. Lambda m into T is equal to constant. So lambda m will be what? B divided by T. B is 2.88 into 10 power minus 3 by temperature is 2880, right? So 2880. So if I cut, I'll get what? If I cut this and this, 2.88 into 1000 is 2800. This goes numerator. So it is 10 power minus 6. 10 power minus 6. 10 power minus 6 meter. If I convert that to nanometer, you know, 1000 into 10 power minus 9. So it's around 1000 nanometer. That means at 1000 nanometer wavelength is maximum. 1000 nanometer. 1000 nanometer means, look at that. So this is where U2 falls. U2, energy U2. Then U1 should be before this, no? This is somewhere U1. U1 is here and U3 must be here. And if you check the options, you can't say U1 is equal to 0. You can't say U3 is equal to 0 either. U1 greater than U2, U2 greater than U1 is correct. Option D is correct. I'll explain it one more time. Read the question again. A black body is at a temperature of 2880 degrees Celsius. Sorry, 2880 Kelvin. Black body is at a temperature of 2880 Kelvin. Right there, you see some relations with what? Wien's displacement law, because 2.88 is Wien's constant, right? So they are trying to tell you that this is related to Wien's law. Anyway, the energy of radiation emitted by the object, the energies are given. For 499 nanometer to 500 nanometer, energy is U1. 999 nanometer to 1000 nanometer, energy is U2. And 1499 nanometer to 1500 nanometer, energy is U3. Okay, all the three energies are given. And then what? Wien's constant is given. Then U10, U2, U10, U30, U1 greater than U2, U2 greater than U1. These are the options. So how do we do this? I need to find maximum wavelength location, maximum wavelength is where. So I can use Wien's. The only option is what? Since wavelength is given, sorry, since temperature is given, and it looks like Wien's constant, it looks similar to Wien's constant, you must be using Wien's law. Lambda m into T is equal to constant. So lambda m is a previous IDJ question. Even though it's a simple question, it's a conceptual question, it's difficult. Lambda m is equal to B divided by T. B is 2.8 into 10 power minus 3 by 2880. And when you cut 2.88 with 2880, 2.88 into 1000 is 2880. So this is 1000 on denominator. 1000, okay? 1000 is taken to numerator. So 10 raised to minus 3. 1000 goes numerator, become 10 raised to minus 3. 10 raised to minus 3 and 10 raised to minus 3, 10 raised to minus 6. But this is to be written as nanometer because everything is given in nano. These are all nanometers, right? So I'm writing them in nanometers. So 1000 into 10 power minus 9. That's correct. 0, 0, 0. 3 zeros are cut. 10 raised to minus 6 again. So this looks like 1000. This is nano. 10 power minus 9 is nano. 10 power minus 9 is nanometers. Look at this. 1000 goes to numerator. It is 10 raised to minus 3. 10 raised to minus 3 and 10 raised to minus 3. 10 raised to minus 6. But I must write this as nano because all these are given in nanometers. 499 nanometers to 500 nanometers. 999 nanometers to 1000 nanometers. 1499 nanometers to 1500 nanometers. So I need to convert this to nano. 1000 into 10 power minus 9. So 1000 nanometers. So I'm sure that maximum falls where? Maximum falls at 1000 nanometers. 1000. This range, no? Maximum. So that must be U2. This is 999. This is 1000. Okay. Look at the wavelength. This is 999. This is 1000. And in that range, maximum falls. And this must be what then? This must be the first one. 499. And this must be 500. And this must be what then? 1499. And this is 1500. And in the first range, you have energy U1. U1 there. In the second range, you have, third range, you have energy U3. U3. Is U1 0? No. Option 1 ruled out. Is U3 0? No. So option 3 is also ruled out. Then between option C and D, it is U1 greater than U2 or U2 greater than U1. U2 is greater than U1. Look at this. This is U1. This is U2. U2 is greater than U1. Did you understand? So that's all regarding transmission of heat. The first module of heat and thermodynamics, transmission of heat. You can expect at least one question from this part. You will definitely get the question if you do whatever we did in class. There are 3 homework questions I gave. I think it was 5, 6, 7. Anyway, I'll send the solutions to those questions. They are easy questions. I'll send the solutions to those questions. If you still have doubts, I can do those in class. So we will meet again in the next session for another module. Till then, stay home, stay safe. Bye-bye. Take care. Thank you.